Hello, I'm Kamal Kodra. I'm a technical market engineer in the Aruba switching business unit. Today in this AOS-CX 10.12 software feature update, I'm going to be covering IPv6 VXLAN updates. This will be part 1 of 2. I'll be covering an overview, use cases, some details and caveats, configuration parts, some best practices, and then completing with a demonstration. So let's go on to the overview. For part 1 of 2, I'll be covering a single fabric with IPv4 in the underlay with IPv6 multicast in the overlay. In a later series, in part 2 of 2, I'll cover a single IPv6 underlay with both IPv4 and IPv6 unicast and multicast in the overlay. So let's first of all cover this single fabric IPv4 underlay with IPv6 multicast in the overlay. First of all, let's talk about what's already in place. So we currently support IPv4 single fabric with IPv4 unicast and multicast in the overlay, as well as supporting IPv4 VSX as well in the overlay. We also support border VTEPs with layer 3, SVIs and routing on ports. You'll also see the term extensions in some of the notes, and this is typically a connection to a non-VXLAN network. Current supported platforms are the 6300, 64, 8100, 8360, 8325, 8400, 9300 and the 10,000. What's new in this 10.12 update for the IPv4 underlay is that we are now introducing IPv6 multicast in the overlay too. We support layer 2 multicast listening, discovery, snooping. We're supporting PIM sparse mode for layer 3, and then we're also supporting IPv6 overlays with VSX and border VTEPs with connections to non-VXLAN networks. So this now means that we're supporting a dual stack, both IPv4 and IPv6 multicast in the VXLAN overlay. And the platforms we are supporting are the same as we were supporting in existing. So the 6300, 6400, 8100, 8360, 8325, 8400, 9300 and the 10,000. Let's go on to the use cases. These use cases are applicable to both IPv4 and an IPv6 underlay and will be related in terms of part 2 of 2. So our first use case, we have a campus with an on-premise DC. We're typically using distributed layer 3 gateways, which is recommended for the campus. And for example, in VLAN 11, here in campus building 1, we have VLAN 11 across the campus, across different VTEPs, i.e. with the 6400 acting as an access VTEP and the 6300 here also acting as a campus VTEP. And you can see we've got VLAN 11 here on both these access VTEPs, and then their gateway is from a V6 perspective FE80:11:11:1, and then we also have, because it's dual stack here, that we can support for v4 10.11.11.11.1. Now in this scenario, sources are typically located in the data center, and we can see in the data center we have a V6 and V4 address with a unique local address starting 2001 in a totally different subnet, but in the same VRF as in the campus, as well as the IPv4 address. Now, typically, if we have this scenario, then we're going to have to be using PIM sparse mode for layer 3 communication between, for instance, VLAN 13 here, one receiver trying to access a source in the DC. However, it is not uncommon to also have sources and receivers in the campus alone, and we can see here, for instance, in VLAN 11 can be a source as well as a receiver in campus building 1, and then receiver can be in campus building 2, looking for those specific sources to play any stream at all. So another important thing is that this overlay can run both IPv4 or IPv6, and is totally independent of the underlay, which can be IPv4 or IPv6. So, as we have stated here, we can have IPv4 or IPv6 in the underlay, and if we're using that, then we're running OSPF version 2 if we're running IPv4, or if we're running IPv6 in the underlay, we're running OSPF v3, and then for control plane we're using IBGP. So next we have a DC use case. We're using distributed layer 3 gateways. For example, on VTEP 1 we have VLAN 10 with an IPv6 address 2001 db8 010:10:10, and similar we have an IPv4 address 10.10.10.10, and then on VTEP 2 we have IPv6 perspective 2001 db8 010:10:10:101, and from a v4 perspective we have 10.10.10.101 in the same VLAN stretched across the DC. And then we have different VLANs on VTEP 3. So some applications in the DC will utilize both IPv4 and IPv6 multicast, and we could have sources and receivers spread across different racks, and hence the use for VXLAN when we're using the same VLAN. We will typically need to have PIM sparse mode because we need to communicate between different subnets as well. Now, a very important thing is MLD and IGMP snooping is required in this setup to limit layer 2 multicast, and this is also the case for the campus use cases that were mentioned earlier. The next use case is layer 3 multicast between VXLAN and non-VXLAN networks, and we're really looking at the right side here of this diagram in terms of representation. Again, we're using distributed layer 3 gateways, which is recommended for the campus, and now we have this border VTEP with layer 3 routing extensions to existing or traditional networks. So here in campus building 2 we have this VSX border VTEP, which is connected to a non-VXLAN network, which happens to have the rendezvous point and bootstrap router. So we can accommodate having both a rendezvous point and bootstrap router in the non-VXLAN network. So that could be an existing RPBSR that you're joining into your VXLAN network, as well as having an RPBSR can also be available in the VXLAN network. And we can also have both sources and receivers in the non-VXLAN network as well as in the VXLAN network, and they can all communicate with each other. Let's go over some of the details and caveats. So the multicast implementation we have here is proprietary, and the fabric for multicast must only include CX switches for VTEPs. We support both layer 2 and layer 3 forwarding for EVPN VXLAN with the Aruba CX switches, and the IPv6 overlay supports Multicast Listener Discovery version 1 and version 2. AOS switches default to version 2 and is backward compatible with version 1. So very important to understand that the layer 2 multicast data streams are sent by sources to VTEPs only to remote VTEPs where there isn't an interested receiver in the same VNI. We must use MLD snooping to stop flooding within that VNI. So our implementation supports only PIM sparse mode for V6. We support border VTEP as I showed earlier in the use case. We do not support multicast over static VXLANs, and we don't support static multicast today. IPv4 MSD and any cast are not supported in a fabric, as well as PVLANs are also not supported in a fabric with multicast. Now let's cover some of the configuration, and this configuration is just specific to IPv4 underlay. Throughout the rest of this update, we'll be using this topology as shown here, where we have access 1 as a specific VTEP and access 2 as a specific VTEP, and we have a root reflector or a spine switch also. And then we have two VNIs. We have an L3 VNI 5001 and an L2 VNI, and then we have all these specific hosts which will also be used in the demo as well. Now the configurations shown will be partial configurations and not whole configurations, so they're very difficult to fit on a whole screen. So we'll be chopping these up and showing important elements. Assume that the user does have some familiarity with some of the basic setups. So in terms of the IPv4 underlay, there's nothing really different from those of you who are experienced with having an IPv4 EVPN underlay in Aruba CX switches. And there's really no multicast going on here, but let's pick out some key points. Well, we need a unique virtual MAC per VTEP, and this configuration is a snippet of access 1 here on the left, and then we do a redistribute of host routes in each VLAN for the type 2, which includes layer 3 VNI route targets and MACs for VRFs. And then moving down, we use for the VXLAN interface, we use the source IP, which is typically a loopback, which is shown on access 1, 192.168.0.150. And then we have the mappings of the layer 2 and layer 3 VNIs. The layer 2s I've mapped VNI 10 to VLAN 10 and VNI 20 to VLAN 20, and then VNI 5001 is a layer 3 VNI, and that's got routing in there, and then we have the processes for both the underlay, which I'm using OSPF, and then we have the control plane where I'm using BGP. So next in the IPv4 underlay, we're going to be introducing VSX, which is shown on this node on the right. So there are some very subtle differences. The first thing that I'd like to point out is that when we're using VSX in a multicast scenario, we must use the redistribute local SVI, or we can do the redistribute local MAC. So when we do have VSX within the fabric, all switches within the fabric that have VTEPs on them must either have the local SVI redistribute or the redistribute local MAC. It depends if you're using layer 2 only, we use the MAC. If you're using layer 2 and layer 3, which typically you are, then we would use the redistribute local SVI, as multicast needs an awareness of system MAC when we're using VSX within the environment. So the next piece that is slightly different is that we have a unique loopback 0 for the EVPN control plane, and that is shown here within the configuration where I have a 192.168.0.161 on the primary VSX access 2, and on the secondary access 2 we have 192.168.0.162 for the unique loopback. However, for the VTEP and effectively the data plane, we use a shared loopback, and you can see that I've got a 192.168.0.160 on both switches as loopback 1, and that 192.168.0.160 is effectively the VTEP address, and that's common across both the VSX primary and secondary. Now we're going to look at configuration that is applicable to both IPv4 and IPv6 in the underlay, or you could look at it as a common overlay. So the first thing that we need to enable is specifically if we don't want to have broadcasts in a layer 2 multicast, we enable IPv6 MLD snooping, and we simply, under the VLAN context, have IPv6 MLD snooping enable, and here it's shown as being enabled on both VLAN 10 and 20 that we have in this topology. I've also shown an IPv6 MLD snooping output. In this setup we have a source group FF38:1:1, which is active, and we can see that in this show MLD snooping we can see an active group that is occurring on VLAN 10. The other addresses that we see are active addresses, and these are because in this specific environment I'm using Microsoft hosts, and default out of the box they do try to look for specific multicast groups, and I've detailed those multicast groups here below, which is for UPnP, multicast DNS, and a link local multicast resolution that Microsoft host try to look for out of the box, which is useful information to know if you have Microsoft hosts within the environment. Now let's look at PIM sparse mode in the overlay with a bootstrap router and a rendezvous point. So the basic is when you have PIM sparse mode, you configure that on the layer 3 interfaces. So you can see that I've enabled IPv6 PIM6 sparse enable on access 1 SVI, VLAN 20 SVI, and we also enable IPv6 MLD enable. And then from a layer 3 perspective, we also have to enable a PIM6 process, and we just enable a router PIM6 in a specific VRF if you've defined a VRF, and then enable it. Now we also do similar on other devices, the SVIs, and you can see on access 2 in VLAN 10 I've done the same thing where I've enabled MLD on the SVI as well as IPv6 PIM6 sparse enable on the SVI, as well as the PIM6 routing process in that VRF green is enabled. Now the next part is to configure the bootstrap router and the rendezvous point. So I'm using a loopback in this instance to be my rendezvous point and bootstrap router, which is loopback 70. I've given it an IP address, IPv6 address, and enabled PIMv6 sparse on that loopback. And then within the routing process for PIM6, you can put in parameters for the bootstrap router and the rendezvous point and add priorities, as well as define the source interface for the BSR and for the rendezvous point. Now please be aware that the priorities for bootstrap and RP are slightly different. So the BSR uses a 0 as the lowest priority and 255 as the highest priority, and its default is 0. And then the RP uses 0 for its highest priority and 255 as its lowest priority, and the default is 192. So I've forced both priorities to be 100 for the BSR and for the RP. So this will effectively force this to be both the BSR and the RP if there were any defaults in place. Now if we wanted to have a backup RP and BSR, you would then configure on a other VTEP the similar configuration, and I've shown in the example below that I haven't put any priorities, and they go in default behavior, where the BSR is defaults to 0 and the RP defaults to 192, so the configuration above will take precedence. Now looking at a similar scenario, however, we're now introducing a BSR and RP within a VSX environment, which is in the fabric. So remember, we don't support any cast. RP is not supported in a fabric here. So if we have VSX in the environment, we use priority for BSR and backup RP, and it's very similar to the previous configuration. We can see that for the primary VSX switch, which is on the left, I have forced 100 for the priority for both BSR and for the RP. And then on the secondary switch, I have defaulted the priority, as in not added any, and that will become my backup. Now also you will have to define a different loop back for each of those, which makes sense if there was a failure of one of those switches. For instance, on primary access 2 I've defined a loopback 71, and then I've simply redistributed that local loopback in BGP within the VRF to make that advertised as would be the case in the secondary, but for brevity I haven't shown that part of the configuration. The next configuration snippet I'd like to look at is when you're using PIM sparse mode with VSX and the VSX VTEP. When you're using VSX, we have to synchronize the multicast states between primary and secondary. So when you're using SVIs on VSX, you have to enable the IPv6 PIM6 sparse VSX virtual neighbor command. Now this is nothing new. This was also similar command for IP when we had IPv4 in the overlay, except it just said PIM. So there's nothing new here. Although it's a new command, the concept is exactly the same. So now I'm going to talk about connectivity. So we talked about the use cases of connecting to non-VXLAN networks. So here we're talking about a layer 2 connection between VXLAN and non-VXLAN networks. So all I'm really doing is I'm extending layer 2 to this non-VXLAN switch. This is layer 2 only. My VTEP I've configured is this VLAN 137, and the hosts in that VLAN also are stretched across to this non-VXLAN VTEP extension as such, and you can see that they are hosts in that same VLAN. So let's look at the configuration. It's nothing really complex. I'll have a lag which extends that VLAN across here, both 113 and 114. I've just shown that in the description. We also have that VLAN across the ISL here too, and then we have the VTEP or the VLAN effectively also configured on both of the primary and secondary. And then on the extension switch, which is just purely layer 2, we have that VLAN going up this lag, and then these devices will be access ports on that switch. So next we're going to cover a layer 3 SVI connection with a multi-chassis lag. So very similar in terms of the multi-chassis lag, except what we're now doing, we're using a transit VLAN effectively between the border VTEP and the extended switch in the non-VXLAN network. So again, the VTEP that we're interested in here is now VLAN 10. We're extending in this example as the transit VLAN with an SVI VLAN 106 across here, and it also exists across the ISL. We have to configure the PIM-v6 sparse VSX virtual neighbor across the SVI. So that was in the in the previous note for when you're using VSX, and then we use active forwarding on that VLAN, so that depending on where we turn up, we don't have to do a lookup. So the configuration is very similar, except that now we've, to the previous example of apart from, we've got an SVI across that lag. So we've allowed VLAN 106 across this multi-chassis lag. We have an ISL with VLAN 106 here too. And then we've just got the SVIs on all of these 3 switches, including the extension. And we have the VSX active forwarding on the VSX switches too. And you'll notice it's in the same /64 in that VLAN, so it's in one SVI. So you could, I've got 2001 host, 2002 and 2003, so they're all in the same subnet. Again, this is just a extract of the configurations and not the whole configurations, but expecting that most people know what the remainder of the configurations look like. Now, finally, we also support point-to-point connections to the non-VXLAN network, so routing on ports or SVIs, and sub-interfaces here. But I've only shown a routing on port example. So now these links between the border VTEP and the aggregation extension are point-to-point links, so they'll all have their own subnet. Then we have another VLAN across here to be able to synchronize information. And then very important is that we now have a new command, which is a new command for V6, but was also applicable when you were doing V4. We have an IPv6 PIM6 sparse data path auto include, and this enables synchronization both between the primary and the secondary, and that is configured between the 2 switches on this VLAN 101. So it's always required when we've got rope or SVI interfaces between the border VTEP and the non-VXLAN network. We support sub-interfaces on these platforms, but it doesn't necessarily mean you would be using these platforms here. So I would say see current recommendations for border VTEPs. We don't obviously things like 6300 and 8100 you shouldn't be really using as border VTEPs in a production environment. And there is a restriction on the 10,000 switch. If you're using it as a BSR and RP, there is a restriction, you can't use it. So let's look at the configuration here. So in terms of the point-to-point links, if we look at the primary here, I've got this IPv6 sparse data path auto include, and this is this VLAN across here. And then similarly, I've got it on the secondary too, in this in the same subnet, and then simply on the uplinks I've just got a routed port on both 114 and 113 respectively, which are in different subnets. And then the extension here, it will be routing layer 3, and it has a default gateway of FE80.137.10.10.10::254, and then you would route locally to get into the fabric. And although the routing isn't shown here, it's a very simple configuration. I've only shown the point-to-point links on 113 and 114, and then I've shown the local interface here, which is the local gateway for the hosts or devices in the non-VXLAN network. And obviously you'd have some routing in between to get these networks between each other, which is not shown. So let's talk about some of the best practices. So I think we've covered a lot of this. So we should enable MLD snooping on all VTEPs, otherwise we're going to get flooding. Ensure the v4 underlay is operational before you start anything. I've gone into detail about why we need redistribute local SVI or local MAC. Only required when you've got VSX VTEPs in the fabric, and you have to use it on all nodes in the fabric when VSX is present on the VTEPs, not in the spines, just on the VTEPs. And use local SVI when you're using layer 3 and layer 2, or if you've only got layer 2 in use, then you use the local MAC. This IP PIM-v6 sparse VSX virtual neighbor command is required when you've got VSX SVIs in lags. Unique virtual MAC should be on all VTEPs when you're using the layer 3 distributed gateway, which is really more of a overall for VXLAN Anycast. Now the RP can be placed in the overlay network or the non-overlay network. Any existing RP in the non-overlay network can be used, and that was shown in the third use case. Now, in terms of where do you put the RP and BSR in a fabric, well, that can depend. There's no real hard and fast answer, and it depends on where your source and distribution is set up. The general recommendation is to put the RP BSR as close to the source as possible, but in practical terms, if you have got a distributed sources, then you sort of have to think about the best placement unique to your own setup. So in terms of RP and BSR support for VSX, we only support the 64, 81, 8325, 8360, 84, 9300. If you're using maybe a small fabric, you can use an RP or BSR in any of the supported platforms from the 6300 upwards if you're testing it, or you've got a very, very small fabric. And then it's not recommended to use this PIM6 sparse VSX virtual neighbor on the point-to-point links or routed on port links that extend to the non-VXLAN network, otherwise you can get data loss. And then we need the PIM-v6 sparse data path auto include when we are using a border VTEP and we have got receivers connected via PTP, SVIs, or routing on ports. And for multicast, I think we've gone through that. We support obviously MLD snooping with sparse mode, and then I've gone through the 3 different extension methods or to connectivity to non-VXLAN networks in the examples with the configurations. So now I'm going to go on to a demo. Okay, so the demo is hopefully you're all familiar with this diagram. So I'm going to have a multicast source FF3811 and I've got an RP loopback 7, which you recognize with a 70-70-70. I've got a stretched VLAN 10 across both of these switches, and that's an L2 VNI. I've also got an L3 VNI. I've created a VLAN 20 as well on this switch, so we can see some L3 VNI information, and I'll go through some of this as we go through the demo. So the first thing we're going to do is so I've logged in, is we just do a show IP route, which we can see that live, so useful to see. So this is obviously the underlay, and I've learnt from OSPF, this is, I know it's my spine loop back, and then I've learnt my remote VTEP got 160. So I'm sitting on this switch, I can see this loop back here, and I can also see this loop back here. So I'm comfortable while my underlay is working as it should be. Next thing to check is can I see some of my host addresses? So we know now where the remote next hop is, this 160 here. And I can see some of my hosts now. So I can see this 2001 DB8 10:10:10:160. And if you can see, that's this host here. So I'm confident from this switch, I can see that host. So it's a good bit of troubleshooting to say, right, I'm confident I can see that. We can also see this loop back as well, 70-70-70 that I mentioned earlier. So you know, we're all cooking with gas here, so we know that's all good. And then just to make it simpler, we can even just filter it on BGP, and we can see those too. Okay, which I showed you earlier. So again, it's worth having a look at some of the L2 VPNs that routes to. So if I just do a L2 VPN, EVPN type 2, and I'm looking for routes coming in from my remote device here, and again, you can see that I've picked up this dual stack host 10.10.10.160, as well as the earlier address from the next hop, and I've also picked up the MAC ending 8F, and you might be able to see that that's the host there. So obviously I'm confident that things are working there as well. It's also worth looking at the type 5 routes as well, so we can see a full prefix. Just make it easier to see. And we can see that I've learnt this loop back to via full prefix by my next hop. So there's some other things that we can do in terms of show MAC address, but I've pulled that up from the layer 2 EVPNs. So I think it's good if we just have a look at the VTEPs to show that they're operational. So I've just done a show interface VTEPs. Let's give us a tiny bit more real estate, make it easier to see.
and we can see that both my VTEPs or VXLAN tunnels are operational, and I've got an VNI 10 and 5001. One's routed and one is not. Okay, so also I'd like to now start some multicast traffic. So before we do, what I'm going to do is we're going to see what multicast we've got arriving at this switch. So a good command is to do a pim VRF pim pending on that specific VRF. And at the moment, we've got these Microsoft groups that are already on the devices, and that's done by default. So what I'm going to do now is on this host here, which is connected to VLAN 10, I'm going to try and get to the multicast source FF38111, but without starting that source. So if I just go onto this device, I'm going to start trying to look for that specific group, and I've already got that configured. I don't know if you can see, hopefully you can see that FF38::1. So this host is connected to this switch. I just repeat that command again. We can now see that I'm now trying to search for that specific group FF38::1::1. And it wasn't there in the previous iteration of that. So now what I'll do is I'll now set off the source from here, and we should join that, and then the pending will disappear because it's no longer pending, it's active. So I've already got this device ready to go. If I hit play, you can see that that started moving. I go back to that host. You can see that this host is now a lot of stuff on this screen to deal with. You can see that I've got this multicast stream that's come here. I can also Wireshark that. You can see the destination, that's the group I'm joining, FF38:1:1, and my source is 2001 DB8101010:160. So that's been successful. Now if I now look at my ping pending, you can see that that group has disappeared because it's no longer a pending. So it's quite a good troubleshooting if you've got sources that maybe not might be sending, or there's some sort of discontinuity. It's a ping pending's a very good command to use. Now next, what I'm going to just show you is the thing I was emphasizing quite a lot was the MLD snooping. So what I'm going to do is I've got a controlled host which is sitting here, and I'm going to switch off MLD snooping on the fabric, and what we'll see is we'll see that the traffic is flooded. That's the only way we can really see that. So that's this host here. So let's get onto that host. Okay, I'm just gonna start the Wireshark up. And then going to VLAN 10 here. You can see I've got MLD snooping enabled, so I'm going to switch that off. Switch that off, go back to that host. Now we can see that I'm now, without having any multicast receiver, I'm not receiving any traffic here because I've not tried to. I'm immediately flooding that traffic on here because I've switched MLD off of that VLAN. So let's switch that back on. Done that. Go back to that host. You'll see that that destination has gone, and now I'll just join. Should already have that configured, so I'm going to try and join. I've joined that. The video stream started, and then the we can see the source and we can see the destination group. So that's the MLD snooping element. Let's exit that. So let's just now have a look at some of the rendezvous point information now. So remember, I've got this RP configured on this switch. I'm now on this switch, which is on the other side of the network. I know it's not a big network, but we can see by doing a show IPv6 PIM RP set, I can see that I've got my RP as I expected, and that's received. So that's good troubleshooting. And then I can do I can actually look at the RP mappings as well. You can, by running the PIM-v6 RP VRF, and you can see that this RP is mapped to that specific group. And then, as we've seen it so often, I know we've got MLD running. I'm just going to show the IPv6 MLD information, and we can see that on VLAN 10 we've got this group that is active, and we've seen that it's being streamed. Now what I'm going to do is I'm going to set off this other host, which is in a different VLAN. So I've got VLAN 10 stretched across here, and then I've got a VLAN 20 which only exists on this device, and I'm going to try and join this multicast group. So let me go across to this device because I want to show you some mRoute information. So is this device here? Get to it. Okay, I must have. It's not. That's the wrong device. Here we are. Excuse me for the slowness of my desktop. So I'm just going to join that same group. I've already got that pre-configured in the player. It should. Okay, we've joined that immediately. Now let's have a look at the mRoute information. So now I've joined that multicast group, we can see some interesting things actually, and I maybe wasn't quite expecting that. So what you will find is that I've got a group address, I've got my source address, and then I'm routing on VLAN 10 and forwarding on VLAN 20. I've also got a stale address which will which will go, it's also coming over the L3 VNI bridged. If I clear IPv6 mRoutes VRF green, that should remove that. Okay, so now we've only got one entry, which is active. And what's happened is that we've got this group coming from that remote source, and it's actually now being routed from VLAN 10 and being forwarded on VLAN 20. So what's actually happening is the traffic is coming across the L2 VNI, and because it is then on, we have the same VLAN across VLAN 10, it's using VLAN 10 and then it's being routed locally. We did get initial traffic across here, but that would age out and it then would come across here. So that's all I wanted to show. So if I actually now shut down VLAN 10 on this switch, so not only have an SVI, which is VLAN 20 here, SVI, which is VLAN 10 here, it's going across the VLAN, it's going across the L3 VNI. Now we will see that that group is being routed. Incoming interface is now VNI 5001, and then it's being forwarded on VLAN 20. And I can switch that by shutting that interface again. So that's all I wanted to do in terms of a demo. It was very quick. There was a lot of stuff to see here, but in the summary, we've shown IPv6 traffic going across both an L2 VNI and L3 VNI with an IPv4 underlay fabric. These are all standalone hosts. So
in terms of additional resources, I'd recommend going to the Aruba support portal at arubanetworks.com and search for the keyword multicast, and that should bring up the latest documentation that covers the IPv6 multicast in the overlay. So that concludes this session. Please watch out for part 2 of 2, where we cover IPv6 underlay with multicast in the overlay. So thank you for watching, and I hope that was useful for you.